is that, that the models of human behavior in travel demand, highway safety, almost any type of data that we can imagine, we assume in traditional statistical models that the betas, the terms that we estimate, are constant over time. And that is that behavior is not necessarily changing over time. But we have to ask ourselves, and I'll give multiple examples in a few slides, is it really correct assuming that an effect of an explanatory variable in a traditional statistical model, is it reasonable to assume that this is going to be constant over time? So when we look at like smart cities and temporal instability, we're going to have rapid introduction of technologies. And we've started to experience that in driving. If you look at how people drive in the last 10 years with all the advanced safety features of cars, things are changing very rapidly. And in addition to that, we have cell phone use and these other things that are causing distractions. Everything is changing at a pace that we've really not seen before in the transportation field. So with smart cities, we have technology associated with smart cities, all the sensors and so on, are likely to adjust traffic signals or whatever, but it in a turn is going to affect and alter human behavior. So we can think of it as human behavior is now going to be influenced by some underlying evolution of behavior, which I'll talk about. And then there's going to be the effect of all these technologies and their interactions with these sort of natural evolutionary forces. So let's talk about what I mean about that. So let's look at the evolution of behavior, and let's look at the case of highway accidents. So just some general background information. Let me see, I think I got it. Just some general background information. If you look at highway accidents, more than 1.2 million people per year, 50 million more injuries are injured. But safety researchers have sought for decades ways to reduce this carnage. And we've come up with statistical models, applied machine learning, and so on. But let's look about what's coming with regard to safety of highway safety and the potential injuries and frequency of injuries that are likely to occur. We have autonomous vehicles, which are obviously going to be key and being launched in the next decade or so. But when we have fully autonomous vehicles, it's going to be a much different scenario, but that's probably 50, 60 years out. The interesting scenario is what's going to happen when we have autonomous vehicles mixing with human-driven vehicles. And there have actually been, I've looked online and there's these little anecdotal things. If you notice an autonomous vehicle, you start developing a sense of how it's going to react to your car movements. When you're looking at another human driver, if you cut off another human driver, you're not sure what the reaction is going to be. But if you look at an autonomous vehicle, and there have actually been some studies that have looked at this, you can cut off an autonomous vehicle and you know that it's not going to ram you in the back or get into road rage and stuff. So you can imagine that your behavior around autonomous vehicles is going to change. It's going to affect the way you drive. Okay, so even though you're not like actively involved, you don't necessarily have an autonomous vehicle, it's going to affect the behavior of all the vehicles around it. So when we add this to connected vehicle communication and vehicle to everything communication, there's a lot of stuff that's coming that could affect how the human drivers respond to these things. So let me get to the next slide here. So if we look at the historical analysis of highway accident data, we really focused on two things: the likelihood of an accident and its resulting injury severity. And undoubtedly, we've been looking at this many decades, and without doubt, some progress has been made. But we look at, if we can sort of think about what's happening, the safety field has struggled with a lot of elements. And I'm going to talk about a number of those, but there are two that I'll start off with. One is there's a general downward trend in fatalities that, notice if you go back, and there's going to be a lot of explanations. I'll go over those in a minute. The other interesting element that has popped up from time to time is that we've noticed that fatalities per distance driven tend to decline in economic downturns and increase in economic upturns. So for whatever reason, there's some sort of behavioral response going on there that we really haven't gotten a full grasp on that, but I'll give you some possible explanations. So let's look at the downward trend in fatalities per distance driven. So you can say, oh yeah, that's obvious why that should be. There's improved vehicle safety technologies, there's improved highway design, there's impaired driver enforcement, all of the things that we've been doing to mitigate the frequency and severity of crashes. You could argue that that would contribute to these fatalities per mile driven going down. But I'm going to make a little case for an additional possibility that is probably in combination with all of these, is what about the effect of possibly temporally changing behavior? Because as people's behavior changes over time, what role does that play in this overall downward trend? So when we get to the economic downturns and economic upturns, we've noticed that you could say, well, this is caused by when there's an economic downturn, there's a change in discretionary driving patterns. There could be changes in values of time, changes in distance that risky drivers drive versus safe drivers, because that could change the accident rate per mile driven. Again, I'm going to say, what about the possible effect of changing behavioral elements that are potentially induced by changing economics? So let's look at this. Other possibility is that many of these changes may be due to some fundamental changes in behavior. And of course, I'll talk about what that means for the models that we use. So let's look at the possibility that human behavior may be evolving and thus fundamentally changing over time, a change that may be in response to short-term and macroeconomic conditions or other time-varying influences. Now, if you go back through the literature, when I wrote this paper, there's a vast body of literature in psychology, neuroscience, economics, cognitive science, and other fields that all sort of mention at some point, and some of it's very old, decades old, that mention this possibility of changing behavior and what might influence that changing behavior. So if we think about how drivers respond to stimuli, or even how, if you're looking more broadly at travel demand, how trips generation might change or activity patterns might change, there's potentially profound implications for the traditional statistical analyses that we've been doing, and even when you get into machine learning and some of the more data-driven methods. So temporal considerations are important in accident data, especially, and I'll talk about other types of data, but in accident data, we don't have all the crashes occurring on a single day, because crashes are rare events, so they accumulate over some time period. So what we look at as cross-sectional data is actually collected over a period of months or years. So all of our crashes are going to be separated by time. In some other surveys that you may conduct in transportation, you may look at like a travel diary the first week of September 2021, and then you do have it sort of captured at a single point in time. But for a lot of the data, we're accumulating it over time. So there's sort of this inherent time element that we have to address. So temporal instability is, for safety analysis, going to be problematic in any traditional accident data that we have. And there have been multiple studies that have shown that there's temporal instability in injury severity and frequency for the period of 2004 to 2012, what happened before, during, and after the Great Recession. And there's even been models that have been developed like Markov switching models that find that there's temporal instability in what you would call cross-sectional data. So we collect accident data over a 1-year period. These Markov switching models tell us that there's week from week, between weeks, adjacent weeks, there's shifting in the betas over time. So the general case for temporal instability is that you can think of it as driver decision-making is made up as a combination of automatic and controlled processes of the brain. So if you go into cognitive science, there's a lot of information on this. These controlled and automatic processes evolve over time based on your accumulated driving experience. So when we estimate our models, we're trying to account for some of this by using variables such as the age of the driver and things like that. But I'll talk about that again in a second. So again, as I mentioned here, you have accident research, attempts to capture this evolution with variables such as age, driver experience. So really what you're trying to capture is what is actually changing as you're accumulating experiences. But obviously everybody is accumulating experiences at a different rate. So age is sort of a gross approximation of what might actually be going on. So if we look at the causes of temporal instability, you have decision-making and cognitive processes that change in eras of rapidly changing vehicle technologies. And social media, everything that we have going on now makes a very strong case for the fact that the betas that we estimate in statistical models are unlikely to be stable from 1 year to the next. And you also have the effect of macroeconomics on risk-taking, which goes back to the observation that the crashes per mile driven changes depending on whether the economic conditions or the aggregate economic conditions are good or bad. And then you also have evolving attitudes and behavior. So I'm going to talk a little bit more about that because that's a little different than these first 2 points. So let's look at the role of changing technology, vehicle technologies first. So we have traditional safety features, which could include anti-lock brakes, electronic stability control. We have the more advanced safety features, autonomous braking, adaptive cruise control. These are starting to being introduced into vehicles. And eventually we're going to have introduction of autonomous vehicles, which are going to affect how everyone else around these autonomous vehicles reacts. When we look at the role of macroeconomics and risk-taking, again, there's quite a bit of literature on this. The literature shows that investment and return experiences, and this means like investment in the stock market and so on, from decades ago can affect your financial risk-taking. And there's also an abundance of information that suggests that your risk-taking in finance in all elements of life could affect how your risk-taking evolves in other aspects of life. So current macroeconomic conditions affect financial risk-taking, and there's a significant positive correlation between financial risk-taking and risky driving. So let's get to this role of attitudes and behavior. Now, this is something because it not only affects what's going on in the transportation field, but also you could use it, think about how it explains what's going on in politics. And when I started looking at the literature on attitudes and behavior and how they might evolve over time, I started uncovering, articles that explain how the sort of society becomes radicalized. There's all sorts of psychological and cognitive science theories on this, but you can think of it as individuals are continuously gathering information from driving, going back to the safety. You're observing others drive, you get social media reports on driving, government reports. So you're always gathering information. You might think airbags are effective or not effective, but you're always gathering this information. And this information is constantly forming and altering attitudes and behavior regarding safety. So the role here is that the relationship, if you go into the literature, the relationship between attitudes and behavior can be tenuous. And the reason is that there's almost always a difference between what your attitude about something is and then what your behavior is. And there's a very famous study by Leon Festinger in 1962, so many years ago. And it's where individuals continually try to reconcile what their attitude is with what their behavior is. So for example, you might have an attitude that global warming is a big problem, but then you might buy an SUV that gets eight miles to the gallon. So how do you reconcile those? So this suggests, though, the sort of theory of cognitive dissonance sort of suggests that there's a constant variation in what the difference between your behaviors and attitudes. And if you look at this, you can look at over time, like in time period 2, the individual is trying to reconcile, getting closer to reconcile the attitudes and behavior. But in time period 1, it's very far apart. And you can imagine this changing over time. Now, I could give a bunch of political examples where this stuff is going on, how abortion in one state and no mask in another. You can see this sort of dissonance between attitudes and behavior, but I won't get it, I won't make it a political speech, although that could be another, or political talk. That could be another completely, very, going along the very similar lines could, be very interesting. But let's look at the non-safety examples. Let me give you some examples of these. So here, to show how opinions change over time, in 2020, I wrote this, I did this little experiment with people's adoptions of autonomous vehicles. So what I asked is, we did this survey. We asked them, how likely would you be to adopt an autonomous vehicle? Then I provided a series of 10 questions that, what do you think about safety? So we asked a question, what do you think, how likely are you to adopt an autonomous vehicle or purchase an autonomous vehicle? You go through these questions that sort of outline all of the potential issues with autonomous vehicle safety and so on. Then I asked the same question again. And within the span of this survey, you could see how the information that was provided between these two questions actually changed their opinion. So here in this 2020 paper, we find that the preferences change significantly. And we also seen a polarization where some people tried to confirm their initial opinion. So you have this confirmation bias. I mean, there's a lot of elements of psychology and stuff that are involved in why that people would do this. But we clearly saw the polarization occur and the selective processing of information. It was amazing what we could get out of this simple survey. So you could see how people process information and how that processing of information will eventually affect their behavior. So let's look at how temporal instability, how all these, I've given you sort of a basis for how sort of ideas could affect our analysis of highway and transportation data. So let's look at how temporal instability, this potential that the betas that we estimate from statistical data changes from one time period to the next, how it could affect the sort of methods that we use. And if you look at the methods that currently dominate the safety field, and truly all transportation fields, we have what I call the heterogeneity models, which are sort of traditional statistical models with mixing distributions, like random parameters, logit, and so on. We have the data-driven approaches, which include, machine learning, neural networks, and so on. We have traditional safety models, which are basically traditional statistical models without the mixing distribution. And then we have what I call causal inference models, which are something that the economists focus on. And I'm going to talk, present some interesting ideas and then talk about those models in a minute, because that's something that we don't use nearly as much in the transportation highway safety field as are used in fields like economics. So let's look at the unobserved heterogeneity models and how they do when you have the betas potentially changing over time. So the heterogeneity models, if you're familiar with econometrics, or even if you're not, I'll try to give you an explanation, but they're random parameter models late in class. The idea is there's elements in the data that you cannot fully capture with the observed variables, so that you introduce a mixing distribution or assume that there's latent groups of individuals that have the same betas. So you introduce these to try to capture things that are missing. But unobserved heterogeneity, has been attributed to unobserved variations in, human behavior, psychology, vehicle characteristics. So usually when you interpret, why am I using this mixing distribution? You're usually because, I don't have the complete information on climate or something's missing. But there's also a possibility that these heterogeneity models will pick up temporal instability, because let's say there really wasn't any unobserved heterogeneity, but if you did have multi-year data and the betas were changing from one year to the next, it would appear as though your mixing distributions would pick up that changing betas over time. So you'd indirectly be picking up temporal instability, but not what you might call traditional sources of unobserved heterogeneity. So let me give you an example. Let's say you have a count model, a Poisson regression, that looks at the number of accidents per year across a highway segment. If the effects of explanatory variables are globally changing over the observation year, that means that a highway segment having more accidents at the beginning of the year is going to have a different parameter value than a highway segment that has more of its accidents at the end of the year. So if we're looking at the number of accidents on a highway segment per year, we're not going to be able to account for that changing beta. If we add a mixing distribution, it's going to say, okay, yeah, the segment that has most of its accidents at the beginning of the year should have this beta, and the segment that has most of its accidents at the end of the year should have a different beta. But that's not because of any unobserved factors associated with those segments of highway. It's really because there's a temporal instability that's going on. So we're unable, we're not able to distinguish between a temporal effect from the true unobserved heterogeneity. Another example, consider an injury severity models of crashes on a highway segment, sort of the same sort of idea. You find statistically significant unobserved heterogeneity, significant parameter variances for one or more of the explanatory variables. But this could entirely be due to temporal shifts, or more likely, and this makes it more difficult to interpret, it's going to be a combination of temporal shifts and then what we would call traditional sources of unobserved heterogeneity. It's like, I don't have a weather variable, so this unobserved heterogeneity is picking up weather effects. When we look at data-driven methods and temporal instability, so you have machine learning, neural networks, decision trees, all sort of the data-driven approaches, what you might call the big data models, they can potentially track existing data very well, but they really do not provide much guidance on how things are going to be changing over time. So this temporal element is usually not addressed in these methods, although when you start using real-time data, you can start getting into some of these elements. So the idea here is to think about the concept of temporal instability and what might be going on, no matter what method you're using. So if we look at traditional models, so these are traditional statistical models without mixing distribution. These are often, you estimate count and severity models. So usually they have very limited data. If you look at the traffic safety field, you do like an empirical Bayes approach for before and after. But if you have temporal instability, these traditional safety models and their potential application in Bayesian before and after analyses are going to be really problematic, because if the betas are actually changing over time, it becomes very difficult to assess what's going on. Now, this last point, these causal inference models, which are very popular in economists, so what economists always argue, that when you estimate a model, you have to make sure that your model is identified, which means that you can understand what's causally going on. And again, the transportation and safety field has really not thought a lot about this, but here's sort of the general concept of what's going on with this causal inference. So one potential problem that not been addressed in the analysis of highway accident data is that those individuals that are involved in accidents may not be a random population of the motor public. So less safe drivers will be overrepresented in accident data. And I'll argue that this can result in erroneous interpretation of findings. Perhaps a good example of this is, what has happened when COVID, so you can imagine when we were in the full lockdown in COVID, the people that were on, that were driving their vehicles, which are the essential workers and so on, that people that still had to drive during COVID lockdown would have much different risk characteristics than the people that drove when there's not a, because now we're getting a subsample of the population. Now, actually, I've collected data on crashes, that happened during COVID, but we're trying to understand how this sort of self-selectivity is that the people that drove during COVID are not a random sample of the population, and any reduction in injury severity or increase in injury severity that we may note may simply be because we are now sampling a different type of drivers. Again, riskier drivers are more likely to get into crashes, and I'll give an example in a second. So you can call this as a selectivity problem because we don't observe, when we observe transportation data, we don't have the full amount of data available because we don't observe everybody driving at all times. So and you can extend this to real-time data because drivers observed at intersections. Or let's say it's like, well, I'm going to avoid this selectivity problem because I'm going to collect data, with remote cameras, and I'm going to look at all the drivers on this intersection. I'm going to observe every driver going through the intersection. I'm not relying on them to have a crash, which would be the riskiest drivers. I'm seeing but you still have this to some extent because drivers observed at intersections or segments, they could self-select. Some drivers say, it's a dangerous intersection. I try to avoid that. So safe drivers may select routes and to avoid dangerous intersections. So you could still have this sort of self-selectivity going on, even in real-time data. So let me give you an example to sort of a nice extreme, especially since we started this talk off talking about motorcycles. So let's consider a model where we estimate motorcycle injury severity. And in that model, we find that rain significantly increases the injury severity. So here, here's a classic selectivity problem. I'm on it, identification problem. The sample of motorcyclists choosing to ride in the rain is a self-selected group of possibly riskier drivers, riders. So for example, I ride a motorcycle. I never ride in the rain. If it's a possibility of raining, I just don't ride that day. So clearly, when it's raining, you're getting a different type of rider. Now, some people, maybe their only mode of transportation, so they have to go, they have to go in the rain. But usually, this concept of selectivity is very evident with the motorcycle and the rain, because it's very clear here that you would have a self-selectivity going on. So when I find that my variable for rain significantly increases injury, I have to ask this third point in this slide is how much of the rain variable is due to actual raining and how much is due to just the self-selectivity that's going on. When it rains, only the riskiest drivers are on the road. So when I look at the injury severities of individual crashes, I notice, whoa, so I'm getting a lot of high injury crashes, but it's just because you're only sampling now the risky drivers because safe drivers are staying home. So to see how important the interpretation of this variable is, if you interpret it that rain actually increases the severity of crashes, you would say, well, I should mandate improved braking, I should make all motorcycles have anti-lock braking systems, I should improve wet traction on friction tires, etc. If you take the other side of it, it's like, well, I think drivers will slow down in the rain and I wouldn't expect much change in the injury severity. The other approach or interpretation policy that you could put in place to satisfy this sort of finding in your statistical model is you could do a public safety campaign about how dangerous it is to ride in wet conditions, trying to emphasize. So you can see here, you have two different policies just by the interpretation of that variable. So when we look at these causal inference models, so this is when you look at the economics field, they focus a lot on this identification issue. And the idea of identification is, I want to know whether it's the rain that's causing the actual precipitation, reduction in friction, whether that's increasing the frequency of crashes, or sorry, the severity of crashes, or if it's actually the fact that the self-selectivity, it's like only the riskiest drivers out there. So the idea with causal inference is it tries to unravel this effect. And that is often done with a control variable approach that undertakes a correction, usually use some ordinary least squares, usually it's done with very aggregate data. But the problem here is that the control variable approach that is used in a lot of economic studies often requires time series data. And if you have time series data and your betas are changing over time, that really brings into the question, how effective is this correction actually? How effective is it in uncovering the true causality? Now, I have one diagram here, and I think my little arrow will point out, you can look at the four methods that I sort of outlined as possible methods to address temporal instability or just to address transportation data in general. So with the data-driven methods, which are machine learning and so on, you have great big data suitability, you have a very good predictive capability, but in terms of causality, you really don't have, of all the methods, it can be a really weak, and that's one of the advantages of statistical methods is potentially they can unravel causality. Of course, if you misspecify, then they can't. At the other extreme, you have the causal inference models, which are not so good on prediction because they use aggregate data. So you're not going to be able to answer a question. It's like, I'm going to increase the shoulder width on this highway from 4 to 6 feet. What's going to happen to the frequency and severity of crashes? You're not going to be able to answer a question like that with the aggregate data. And they're not very suitable for big data, but they do potentially unravel the causality. So you can, if you structure the data correctly, you are going to be able to tell if the increase in severity of crashes for motorcyclists is actually due to rain or a self-selectivity process that's going on. Then the traditional safety models look at this like blue line, and the heterogeneity models basically expand out the traditional, they just give a lot more flexibility to the traditional safety models. So if you want to look at sort of an overview of where everything stands, this diagram sort of relates the prediction, causality, and data size trade-offs between the four methods that I talked about. So how might you address temporal instability? And this is, it's not an easy problem to solve, especially when you have this potential selectivity problem. Now, let me quickly go back. When, I mentioned that when you have a model with selectivity, there's actually a mathematical way to correct for selectivity. And in fact, James Heckman shared the Nobel Prize in 2000 with Dan McFadden, the Nobel Prize in Economics, for developing a selectivity correction. So the fact, so the idea is that I do not observe all of the drivers having crashes, and you're not going to design an experiment. Well, it's like, hey, could you crash into that tree so I could collect information? So you would have everybody observed in a crash. Since you're not going to be able to design that experiment, James Heckman developed a method where you could correct for that selectivity bias, so you don't actually have to observe it. But unfortunately, that correction, it only works for a simple linear model, ordinary least squares. Applying that to a nonlinear model is an econometric nightmare. So that's why economists have simplified things using aggregate data to try to solve the identification process instead of using very detailed disaggregate data and using a Heckman style correction. So potentially or theoretically, models, very complex nonlinear mixing models, could be corrected for selectivity bias, but the mathematics are just beyond our grasp. And with the introduction of machine learning and other methods, it's clear that we're going to have some hybrid system to be able to resolve all these issues. So let's look at addressing temporal instability. How would you do that in a statistical model? Well, there are a lot of ways. You'd have to have very detailed data, but one is to develop a model that tracks the changes in estimated parameters over time. So you can make the betas as some function of time. You could also introduce heterogeneity in the means and the variances and have them track temporally over time. So that's a possibility. You could look at estimate, Markov switching models. But I can tell you these Markov switching models, although they have great intellectual appeal because you can move from one state to another almost continuously over time, or move into between multiple states. But I can tell you the mathematics of implementing that model and the estimation that required, it's extremely difficult. So my guess is that machine learning is going to be a much easier way to uncover some of these complexities. But these state transitions, if you use Markov switching, the state transitions can also be functions of time shifting explanatory variables. Although I can tell you the Markov switching models that I've estimated, even with two states, you have to use all sorts of these Bayesian techniques to do the likelihood function. It's a very difficult process. But theoretically, you can imagine, yes, the transitions between states could be functions of time varying variables. So what are sort of the summary and conclusions? Thinking about, there are 2 points that you should think about coming from this. One is, yes, the betas could be changing over time. How's that going to affect my results? And the other is, because this is something the transportation field has to think much more about, is what's going on with this self-selectivity. A lot of times we don't realize the data that we collect is a self-selected sample. So if you collect data from people that have crashed, you're not observing the people that don't crash. Now, whether they have significantly different, crash behaviors, we don't know for sure, but they probably have some difference. And if you observe traffic at one intersection, that's self-selected because it depends on the people that choose that route and go through that intersection. So those are things you can keep in the back of your mind, and they could potentially help you explain model findings. So for example, with the motorcycle example, when I came up with the rain indicator variable, I could explain that 2 ways, right? You could explain it, yes, rain reduces friction, causes more severe crashes, or no, rain causes the safe people to stay at home. I'm observing the riskiest drivers. They have more severe crashes no matter what the weather condition is. So there's 2 ways of looking at that. So the temporal elements associated with individual behavior are important factors to consider. And ignoring these fundamental temporal elements can lead to erroneous conclusions and ineffective or dangerous safety policies. So for example, the one I gave with the motorcycles, if you just had a public campaign, you didn't account for the anti-lock braking, you would have 2 different policies that could be, I think in the motorcycle case, both policies would improve safety to some degree, but the efficiency of one policy versus the other would depend on how you interpreted that variable. So you could, if you look at the different analysis methods, and I sort of came up with 4 here, they're all affected by temporal instability in different ways. So no matter which analytic method you're using, you should give careful consideration to the interpretation of results. So for highway safety, the possibility of temporal instability will be much higher in the world of partial autonomous vehicle adoption. And you can think of this for smart cities and so on. All of the information is going to significantly change how people behave. So the betas are definitely going to be changing over time. So this has profound implications for current safety practices, because the things that we're doing now are probably not going to translate very well into a future environment. So while explicitly accounting for temporal elements in current modeling approaches is a formidable technical challenge, as a field, we have to keep thinking about the temporal instability, self-selectivity. We have to keep thinking about these sort of higher level processes as we develop our statistical models or apply machine learning. So this is something that I hope everybody gets from the talk. Think about the possibility that human behavior is changing in a fundamental way over time. And I think there's very strong evidence for that, especially in today's environment. And then also think about this whole notion of self-selectivity, because a lot of times people don't even think of, what is this idea of self-selectivity? I'll give you an example. The first class, and I teach a statistics and econometric class, and the first class we do is we have 151 people that choose one of three routes. And I try to explain, and you predict the average travel speed on this route. So you predict a simple regression model that predicts the average travel speed on the route, and it'll be a function of the volume on that route, the number of traffic lights on that route, and so on. But I mentioned that the routes are a freeway route, an arterial, and a rural road. And then I mentioned to the students that there's actually a selectivity problem here, because you only observe people going on one of the three routes. And so the fastest drivers are probably going to go on the freeway, right? So if you close the freeway, all the betas that you estimated are not going to be able to predict the speed of what the drivers on the other two routes are, because the freeway drivers are the fastest riders. So this notion of self-selectivity is something that we have to think about, I think, as a profession in transportation. The economists, I think, probably go overboard on this, but we haven't really thought about it as much as we probably should. So I guess there I can stop sharing, and I would be open to any questions, comments, or whatever. I should tell you that I'm in the students are in the process of handing that first assignment in. I think it's due on Wednesday. That's why I brought it up here. I told them that your models are going to be wrong because of the self-selectivity yet, but since this is the first class, because there you can actually use a James Heckman style correction because it's a simple linear model. But just getting that concept in mind, a lot of people wouldn't think about the fact that since you're only observing drivers that crash, we don't know how drivers that didn't crash, what the severity of the crashes would be. So, any questions?
Thank you, Professor Mani. I believe there is a question on the chat box.
Right. Actually, I was going to ask this question because I and Rakib have discussed it for TRB. Okay. So Rakib, who has just appeared on the screen now, is my PhD student, and he's in his first year, and he had this thinking about basically risk homeostasis.
Oh yes.
So he wanted to see how the COVID affected driver behavior and therefore safety from this point of view. People will compensate for their behavior. Maybe the conditions are better during COVID because less cars, so people will become more riskier. And he tried to prove it by data on I4. And Rakib, if you want to follow up on this line of thinking, I think he didn't find significant effect. And he was a little bit disappointed, but maybe this touches on it's not really maybe it's a temporal thing, the time effect, but it is also the risk compensation issue. Rakib, do you want to maybe mention anything so that maybe you can hear Fred's feedback?
Yeah, so as Dr. Atif was saying, so actually there is some observation who are very close to the theory of Sam Pearsman. However, I'm not sure whether it should be or how it should be. The models are not getting, we're not getting significant outcome from the model. So that's why we're really confused. So how should we actually proceed? So,
but Fred answered the question in the presentation because you did not account for the changes by time.
maybe.
Okay.
So that's I'm not you. So you wrote in the chat the Peltzman paper, is that right?
Yes, yes.
I'm not sure. Let me share my screen. I'm not sure if did you happen to see this paper that I wrote in the Journal of Risk and Uncertainty in 2006? So you might look at that or send me an email and I can send it to you. But here we looked at, and actually we did account for the self-selectivity in this paper. So I'm not sure how it would apply. So let me give you the idea of what we did in this paper. Is we looked at people in the early 1990s that bought cars with airbags and anti-lock brakes. And what we did, following the accident history of people for 6-7 years, I can't remember the number now, we looked at how their accidents changed after they bought how their accident probabilities change after they bought cars. And we found in this paper that we argued that safety features such as airbags and anti-lock brakes were really not. Can you show you some of the, actually we did the models here. We actually did account for the self-selectivity, but what we found, and it's also interesting that when this paper came out, I was actually on Good Morning America talking about it. So I think if you go to my website, I have the link where I talk about it on Good Morning America. But this is a very interesting thing. We found that anti-lock brakes and airbags, that people just tended to drive faster. So the idea was, and this is sort of the Peltzman theory, is I like to have a 1 in 10,000. I'm happy with a 1 in 10,000 chance of dying in a crash. So if you make it 1 in 40,000, I'm just going to drive faster, or I'm going to, start using my cell phone to distract. So eventually to try to get to the 1 in 10,000 chance again. And when I gave this interview on Good Morning America, they were looking at the effects of side impact airbags. Now, so this is sort of a similar situation, is there's a self-selectivity that people that buy side impact airbags first are the safest drivers, right? Because people that are the safest drivers will seek out the most advanced safety features. So when the National Highway Traffic Safety Administration estimates the effectiveness of driver side impact airbags, they look at crashes with side impact airbags and crashes without side impact airbags, and they say, okay, they're 50% effective reducing fatalities. But what they find out is that as you go year and years past, you find that the effectiveness becomes less and less. And the reason why the effectiveness becomes less and less is that as you get further along, you suddenly observe the riskiest drivers starting to use the cars with side impact airbags. And they're not going to be nearly as effective as the safe drivers. Because if you say, I have this spike on the steering wheel, and you give it to all the safest drivers, it's going to, wow, this spike on my steering wheel that pokes my head when I have a crash is very effective in reducing. But it's only because the safest drivers. So there's that notion of self-selectivity that we try to address in this paper. So you might glance at this paper. It's probably not going to be, like directly applicable to what you did, but it may give you some ideas about what to think about. And of course, I would, be happy to, talk to you about that afterwards. Yeah, but that is a very, and it's interesting in that interview, the person that was from the National Highway Traffic Safety Administration just said that we looked at people with, this, and we looked at people without, and we found that they're very effective. That's exactly what you don't want to do, because the people that have them are not a random sample of the population. They're the safest drivers. So you're going to overestimate. The only way you can truly find the effectiveness is to have everybody use them. And then you will know that how effective they are in the crashes. So it's an interesting concept.
Samuel, if you allow me to follow up, please, because you already told us, Fred, that particularly that during the COVID, you reuse the same example, is that it is self-selected group that is driving during the COVID, right?
Yeah.
So we looked at the data, I think 2019 and 2020.
From 2017 to 2020. So we considered
Right, but this is a lot of before, but basically, COVID came toward the end of
19 and 20, yes.
Beginning to 20. So if you look, let's look at 19 and 20, the last 2 years of crash data, there were a couple of peaks, right? If you look at the CDC charts or the Johns Hopkins, you find we had like a peak around maybe March 2020, then another peak towards summer, and then Thanksgiving again, right? So we had these up and downs, and then overlay over it when the government intervened with some mandates and when the government pulled back. So it's a kind of complex, right? And apparently the people that drive, as you said, Fred, they are self-selected during these, I'm not sure during the peaks or during the government mandates only. Mm-hmm. So we have on and off, on and off, and then so maybe here definitely want to look at at least a monthly crash pattern, right? Not even yearly, because the yearly is going to disguise all this, right?
And what you really want to know is, how has the driving population changed? So actually, I'm sending out a survey, and this sort of tries to get this. We're sending out a survey in a week or so that sort of asks people during COVID, how did your travel change? It went up or down. So we're going to see and then we'll be able to associate that with all of their socioeconomic characteristics. But to really be able to answer, because you do have this self-selectivity going on, is you have to know who's driving, how the drivers have been changing during this period. And even though that data is going to be very difficult to get, when you come up with your findings, you could say, well, this could be picking up, and sort of like what Dr. Abdelatif was saying, is that this could be picking up, variations in who's actually driving. So now you have these risks. Maybe essential workers tend to have higher crash rates than the general population. I don't know. So when the essential workers sort of dominate the road, then you're going to have more severe crashes, and the frequencies are going to change. And you also have, as a complicating factor, congestion tends to, change the frequency and severity of crashes too. So you have that fluctuating as well. But this self-selectivity, what makes COVID such an interesting experiment is that we know that during COVID, the population that's driving is much different than the population we typically are driving, much different. So if there's any of this sort of self-selectivity going on where, that's because riskier drivers are driving during the rain and safer drivers don't drive during the rain, we're going to pick that up in COVID. But unfortunately, that it's not easy to capture what's going on, because we don't have these like travel diaries that we were simultaneously collecting during COVID or something. Right. But still, there are probably things you can do with the data that we typically collect.
Yeah, thank you so much, Professor.
From the audience.
So I'm getting some questions in the chat. Can somebody maybe read that?
I can read. So there was a comment about, we also observe change in human behavior for ride sharing, Uber.
Yes.
A comment from Arif Satri. There's a question from Nafis Anwari. Is there a possibility that during the first month after lockdown ended, when things were reopened again, people's driving skills became worse?
Yes, that's definitely, there's a classic is a motorcyclist, because in northern states, motorcyclists don't ride for like 6 months, because it's snowing and so on. And there's a lot of evidence that shows when they first get back on the motorcycle, you get a lot of crashes, like in the first month of spring, because you forget how, your assessment of stopping distances, everything is different. So that's definitely a possibility. And you may notice this. I noticed this when I was in Seattle. Seattle is actually very dry in the summer. And I think this year they went like 55 days without any rain. But what happens, interestingly, is the first rain after a long no rain spell, you get a lot of crashes, much. And some of it is due to the unfamiliarity. And then I think there's actually some physical aspect of it, is that the initial rain brings up the oils from the pavement. There's actually some physical thing that makes the friction worse. But most of it is just behavior, that you forget how to drive in the rain, right? Because you haven't experienced it for 55 days. It's like you're in Seattle. How could you forget about how to drive in the rain? But it's amazing. I think there's probably a lot to that, is if you're not driving nearly as much, it's amazing how quickly your skills might deteriorate. But you would recalibrate probably within a couple drives, but you would think that those first couple drives coming back would be unusually dangerous. So that's a good point.
So another question came in. You said that the self-selection of crash data has a higher bias towards unsafe drivers, but within that subset of data, the biggest subset of the users we are trying to solve this safety problem for in the first place?
Now that's, the question, actually, my dissertation advisor, Cliff Winston, who's a senior fellow at Brookings, he always tells me that, your models are not identified, because he's an economist. Because of this self-selectivity, your models are not identified. And so he's actually writing a paper on this. It's going to be at some point published in Transportation Research Part B. And Chandra Bhatt and I are writing a rebuttal against his paper. So that's going to be a fascinating thing to read when that comes down. It should be like 6 months or so. So, but here's the idea, is that we know that the people that are involved in crashes may be unsafe, but they may not be. I mean, because crashes are pretty random. You can have the safest driver in the world can still get crashed into. So I'm not sure. It's not like when economists use the selectivity example, they look at like SAT scores and which university you go to. So they don't observe anyone with a math verbal score of 800 going to MIT, because you just don't. So there, it's very clear. The self-selectivity is very clear. In our case, we actually do observe very safe drivers in crashes. They may be less likely to be in a crash than a riskier driver, but we do actually have those observations. And you could argue that the heterogeneity models account for that to some degree, because if you have a riskier driver, you'll have a different beta than a safe driver, but it's not going to be able to track that perfectly like you could if you were doing a full selectivity correction. But heterogeneity models can hide a lot of that, at least account for some of that self-selectivity. But, that's a good point, is we really don't know how bad our, the assumption that we're getting a random sample population is. I mean, it is possible that the people that we observe in crashes are pretty much close to a random sample, but it's likely that you would just think intellectually that riskier drivers are more likely to be in crashes. But nobody's really explored that because, again, you can't conduct experiments with people saying, okay, everybody's going to run into this tree and then I'm going to collect all the data, because you only observe, you can't conduct an empirical experiment like that.
So the concept of quasi-induced exposure is basically relevant, which you know assume that the guilty driver is self-selected because it's the risky group, and the innocent driver is random.
Yeah.
It's a random. They're still involved in crashes, but they are random because they are, you know. So you can split your data into two groups.
Yeah. No, that's a good point.
Yeah.
So let's see.
One question about this data-driven methods techniques. Like, I'm wondering if the clustering of the data into different categories can ensure to explain that instability.
Yeah, this is actually a very good and very fascinating question. And there was one paper that I wrote recently that it looked at temporal instability, but what it found, I can't. Yeah, let me do. It was like, I can't remember exactly, but there were two groups of drivers. Let me use as an example, drivers that were in crashes that were drug crashes or non-drug crashes. So I split this sample into two groups of drivers. It wasn't drugs. For one group, the temporal instability was off the charts, from year to year. For the other group, it was significant, but not nearly as significant. So what this suggests, and I actually talked to Bill Green, the developer of NLogit, to see how we might model this. This suggests that a lot of the instability that we may notice in crash data or any kind of transportation data may be driven by a small portion of the population. So what I thought would be really interesting, and maybe somebody in this crowd can come up with, oh yeah, this is a cool idea, is that you could have like a latent class model where one class is temporally unstable and the other class is stable. Because I have not developed the econometrics for this yet, but I suspect that a lot of the temporal instability that we find in data is probably driven by a subpopulation of like 10 or 15% of the population. Their betas are changing so rapidly, it looks like everybody's beta is. So that would be a fascinating thing to see if there is some subpopulation where the betas are constant. Now, if you think about the mathematics involved in constructing a latent class model where you have one latent class that has the same betas for all the years and another latent class that has different betas for each year of crash data, it's not like ridiculously complex, but that if anyone's interested in doing that, they should send me an email. That'd be an interesting paper. Because then you could show that there's temporal instability is driven by a subpopulation of drivers, and that would be fascinating.
Any other question?
May I ask a question?
Oh yeah, that was it. Somebody mentioned the aggressive drivers and non-aggressive. So yeah, I think it was the aggressive drivers had obvious temporal instability. The non-aggressive drivers was very marginal. And that sort of got the idea that maybe these aggressive drivers have such erratic behavior that they're just, that there is a subselection that might be aggressive drivers and some others that are driving this whole process.
Okay, Dr. Guo, you're asking a question.
Yeah, hi, Dr. Manning. Thank you so much for the talk. I actually have two questions. One is about self-selection. So I also do a little bit about statistical modeling, and self-selection is obviously one of the kind of challenging thing for me to interpret. And the reason is because sometimes, even though I know it's self-selected, but there are contradictory explanation. For example, if you think about the rain example, people driving in the rain may be more skillful, right? They are confident, they know they can handle the rain. And on the other hand, they are, as you say, they are more risky and they probably have more accident. There are many other examples like that. And I'm just wondering, in that case, how can we handle that? We need to have some interpretation. And is there any way without collecting the data we can like test one or the other, or it's case by case? Yeah.
So yeah, that's a very good point. And I guess the only way to really, because as you mentioned, if you are a very skilled driver, and there's also some risk compensation that's going on in the rain too, right? So some people, and I think I have a paper where I did a little graph on the effect of weather. So when it rains, that introduces some people, so your risk is changing because of the rain. Some people may slow down just the perfect amount so that their probability of the crash is the same. Some may not slow down enough, which makes them more likely to get it. And then some may actually drive safer in the rain, because they owe it grossly. So unfortunately, unless you use sort of a James Heckman style correction, which again would only work for a linear model, it's really hard to determine which of those effects is coming in. So I would, I think recognizing the possibility that there could be these multiple effects and maybe discussing that in the paper is probably the best we can do now, without developing a Heckman style correction for a nonlinear model, which is, even for linear models, the Heckman style correction gets messy when you get into multinomial choices. But it's and this is why, economists, we got this. So what they do is they just aggregate the data and then start using fixed effects over time to try to resolve this problem. But by aggregating the data, you're losing all these very interesting points. Yeah. So it's a very difficult problem, but I think that's sort of right at the cutting edge of where the field is. It's like, how can you explain what's going on? But a lot of people don't even recognize that self-selectivity is an issue. So I can't give you a method to tell which one is which, but speculating is like, well, it could be because of this, it could be because of that. That helps a lot, because eventually somebody will pick it up and say, I can do a semi-Markovian process and maybe figure something out.
Got it. Thank you so much. And may I follow up a quick question? Another question is about the temporal instability. So I learned when I took some course for the discrete choice modeling and statistical modeling, the time series obviously is trying to handle the change over time. And I guess the difference is one is changing beta, one is changing X. So I'm wondering, are they equivalent, right? For example, if you can capture some macroeconomic variables like changing over X, and you can assuming those beta probably is fixed, but just because the X is changing over time. So is it the same treatment or can achieve the similar results?
So that's an interesting point, is that the change over time caused by a change in X or caused by a change of beta. And probably realistically, it's caused by both, but it's almost impossible to separate those effects out. And for time series analysis, a lot of times you just try to pick up sort of these aggregate trends. There's some value there, but most of the work that we do is with cross-sectional, or what we like to think is of cross-sectional data. But it's difficult. That's one of the difficult points, is to try to unravel what is the actual change in X. Now, as I sort of mentioned, it is possible to have your betas be functions of X's that are changing over time, in addition to having an X. It's possible to structure, even with the analytic methods that we have available now, even like in NLogit and stuff, it's possible to structure your data like that. That might try to, uncover some of those differences. So, but again, that's something that would be sort of cutting edge, but that's what you try to focus on, is how do you find or developing an equation for how beta might change over time with some data set that you have over a multi-year period. Could be very, very interesting.
Thank you so much. And I also want to thanks for your textbook, highway engineering. So I'm also very addicted to that. I teach also the highway engineering course over here. Thank you so much for that.
Oh, great. Yeah, that's so you're using the 7th edition now, the latest?
I think so. The newest version, 7th edition.
Those pictures, I should mention, I think the picture on the 5th edition, which is a little old now, that's actually downtown Orlando, because my friend Scott Washburn, who's at UF, took that. But the last 2 editions are pictures in Tampa. So if you're ever wondering what the covers are, they're. And then I think before that, the 4th edition was a picture in Seattle, because I first wrote the textbook when I was at the University of Washington, and my friend Scott Washburn, who's a professor at UF, also he was a graduate student at the University of Washington in that time. So that sort of gives you the cover stories.
That's great. Thank you so much. Yeah.
Great.
Thank you. Thank you, Dr. Manning. Dr. Ati, would you like to conclude concluding remark or?
Yes, I guess people are leaving, you know, Vikash left, Essam left, Naveen left. so the people I wanted to introduce, Fred, guys, if you, you know, we are done with the seminar. If you want to stay around, you know, stay 5 minutes. If you want to show yourself, we can take a screenshot of all of us for memory with Fred. But basically, I wanted to introduce, so the way, so Fred, when I became chair 8 years ago, you remember I was the junior faculty in transportation. Essam was the chair, and then Haytham came. And then after I became the chair, Essam retired, and we hired, before he retired, we hired Naveen. Naveen now is a full professor. And then we hired Samuel on his way to become an associate professor. And then we hired, then we started the smart city initiatives. So we shifted a little bit the focus into technology, and you know, we call them smart city